Get started to respect everybody's time who's here. And if anybody does join late, they'll be able to catch up, I think. So I'll start with a brief introduction of myself. Thank you all so much for joining today. My name is Carey, and I'm going to be talking today about Monte Carlo methods in the context of exploring stochastic equations. And specifically, we're going to look at an example of estimating insurance risk of a portfolio. So we're going to walk through that, and we're going to do it using something called the Anaconda Python distribution. So it's going to be using the software language called Python, and specifically a data science flavored distribution of Python called the Anaconda Python distribution. So I'll go ahead and show everybody real quick what that looks like. We should all be able to see my screen right now. Let me double check that. Yeah, so we should be showing the screen. What we can do is say, if I come up here and I were to click Anaconda Python distribution, that's what we're going to be using today. This is an open source version of Python that you can all download and use for free on your computers, commonly used in data science applications. There are some paid versions, but if you click through and you go to their products, you can see that there is an open source version of this distribution, and that's what I'm using. Also associated with that is the Conda package environment manager. This is like a virtual environments for Python. And this is the way that we can install different packages that we might use in machine learning or Bayesian inference or things like that. So if you wanted to follow along with this or sort of replicate it yourself, I'm happy to provide the Jupyter notebook, which is sort of the source content of it at a later time. And we're going to be walking through that. If you were to click this download button, you can download this free open source Anaconda version. After you get it installed, I'll show you how to launch it real quick. I typically just type in ANA for Anaconda prompt here, and it will launch a little shell, the Anaconda prompt. So I just typed in ANA and my Windows Start to launch the Anaconda prompt. And we have this base environment. If I then were to type in Jupyter space lab, LAB, that's going to launch an environment, a Jupyter Notebook environment, where I can start to run code. After you hit enter and you launch Jupyter Lab, this thing launches here. And this is sort of like our IDE, really, although it's appropriate for interacting with remote code as well. So that's what I'm going to be using to walk through in case you're curious. If you want to set this up yourself, you should be able to do it. Just quickly Google, Anaconda, Jupyter Lab. You'll find some tutorials for how to get this software installed. So after we get it installed, I can navigate to wherever it is, different notebooks of interest. And today we're going to be walking through this Monte Carlo methods notebook and this Monte Carlo simulation. This actually gives us a live coding environment, so I can run this code and change it and type it in all these code chunks. What I'm going to go ahead and teach from today is a downloaded version of this document, which is an HTML document. But it's basically the same thing. It's got the Python code and the output, but this is a little bit easier to see from a presentation perspective. All right, so I'm going to go and get started with the content in just a moment. Does anybody have any questions before we get started? You can post a question in the questions window. I'd be happy to answer it. All right. I'm not seeing any questions yet, which is fine. I'm going to go ahead and get started. I'm going to pause my webcam. I think it's a little distracting sometimes to see the face, but I did want to say hi to everybody first. And now we'll just go ahead and focus on the screen. All right, so the topic for today is simulating data systems with NumPy using Monte Carlo methods. So Monte Carlo methods has a nice history from the Monte Carlo casino to understand distributions of potential outcomes. And that's sort of where that nomenclature comes from. What we're going to talk about today is using these sort of simulation approaches and specifying what we'll call stochastic equations to understand how uncertainty in inputs affects our final outputs. And specifically, we're going to do this in the context of insurance claims with a presumed distribution of probability of claims occurring and of claim amounts. So we're going to do this with Python, and we're going to use a couple of libraries of interest. We're going to use NumPy to generate some samples. NumPy is our matrix algebra library in Python that also includes a lot of statistical functionality, including random number generation. And then we're going to use the vectorized nature of NumPy to generate a bunch of random samples and summarize them and plot them and view them to understand how the risk of payouts changes as a function of the inputs of this stochastic equation. At the top of all my notebooks, I'll almost always start with some library statements and pull the version informations. Sometimes we get different behavior. You know, Python is open source. A lot of these libraries are changing over time. And so I like to include these versions so that you know what's going on. So this is Python 3.8.3. That's the Pandas version, that's the Matplot version, that's the NumPy version. If you ever see slightly different behavior in the code you're running from what you see in this notebook, the reason could be due to these different versions. I include some other options at the top to try to make these notebooks look better as they render. And you don't always need to do this, but it just makes it look a little bit nicer. And now we're going to get into the actual content. So let's assume that we're in the context of working for an insurance company, and we want to be able to understand how much we should charge for a group of customers based on some historical data. And we're going to try to sort out what a reasonable premium would be. So I'm going to walk through this in some very simple ways and then some in increasingly complex ways to illustrate the difference between deterministic and stochastic equation approaches to this. And at the end, we'll talk about a little bit of extensions into Bayesian inference that kind of goes along with this stochastic equation. So if this is our task, it seems like a pretty easy task. We know in our historical data the average probability that a customer will make a claim, right? We could just look back over the last 2 years and say, what's the average probability a customer will make a claim? And we know that the average claim amount each customer makes if they made a claim, these are all things we could observe. So we might exclude the 0 claims and say of the claims that occurred, what was their cost distribution? We could calculate the average of those numbers. So if we did that, we could simply use those averages to then forecast forward what the expected costs will be for this portfolio of customers. So I've written some basic Python code to do that. We've got the size of the portfolio is 200 people. Our claim probability is 5%, and the average claim amount is $2,000 for a claim. I'm sort of picking those numbers out. So if we do this, it's fairly straightforward to generate the expected cost of the portfolio, right? The average cost by simply multiplying these things together. So the payout across those customers would be the number insured times the claim probability times the expected average. And that's going to simply be $20,000 here. Now that seems really simplistic, but I think it's important to make the point that if all we do is study the average, if all we do is study the mean, this is essentially what we're doing. So if I were to fit very fancy regression models in a frequentist framework, that's the sort of like linear regressions where we generate p-values and things like that. Generally, what I'm doing is estimating means. I'm estimating the middle, the average. And when I forecast forward, I'm going to forecast my estimate of the mean, right, of the average, the expected value of the distribution. That is very simply represented here, but even when we do more complex regressions, that's the sort of thing we're typically doing. You know, if your outcome is the expected value of a distribution, you're estimating the mean, which seems overly simple, and we'll see in a moment that it probably is. So if I wanted to estimate this expected mean, I could do so, and my payout's $20,000 total across this portfolio. I give it a fancier model where perhaps my claim probability is conditional on other things like things I'm allowed to price on, or even things I'm not allowed to price on, but I observe just to get a better forecast of the cost of the portfolio. The claim amount could also depend on other things like type of car people drive, their age, their credit score, all of those sorts of things. But at the end of all of that, I'm still estimating the average expected payout and reporting it, potentially with a confidence interval. So when I'm done with that, even if I've done a bit of portfolio management through some linear models, I end up with an estimate of the expected payout for the portfolio. And if I wanted to assume that I want to make a 20% profit over the total payouts, I could simply calculate the premiums I need to charge across the full portfolio based on my expected payouts, right? So if we did times 1.0, we would be exactly covering costs. Times 1.2 would give me a 20% profit over those costs. And I've written the basic Python code to do that here. So our premium then per person would be $120 as expected. So this seems really simple, and it's a good place to start to then move forward into what I would call stochastic models. This is a version of a deterministic model where we're really just thinking in terms of specific means without thinking about the underlying distributions and variation of those modeling inputs. Our expected revenue is going to be premium times our number insured, 24,000, and then our profits would be the revenue minus our expected costs of 4,000, which is of course our 20% expected profit margin across this group. Okay, so I can now report back and say, okay, we looked at last year's data. I have a conditional expectation of the probability of claims occurring. I have a conditional expectation of the amount we would pay out for each claim, and I add all of those together. And if we set our premiums at this price, now we'll have a given profit margin. And it's true that you should expect to have that if your model is correct on average across a large number of replications. But that does not adequately capture the risk of the underlying variability. So on average, if we did this every year for 20 years, our average profits would be 4,000, but there are years in which they might be lower than 4,000 or higher than 4,000. And furthermore, there might be years in which they are negative, we actually lose money, right? So if all we do is study the middle of the distribution, the averages, the expected values, we lose track of that variability. So what we're going to think about today in the focus of this is to really talk about thinking in terms of distributions as opposed to averages, and then how we implement that in a basic Monte Carlo simulation with Python. At the very end, I'll give some thoughts on how we might implement that in a modeling framework using Bayesian inference. We could talk a little bit more about that as well. All right, so how do we overcome this? Well, the answer is implement stochastic equations, not deterministic equations. And we're going to use Monte Carlo simulations from those stochastic equations to study the distribution of potential outcomes, assuming under the assumptions we've made for the stochastic equations. So we'll get a distribution of potential outcomes, and then we can summarize those potential outcomes in ways that are meaningful to the business. That allows us to examine the variation, not just the means. Okay, so overcoming the average, thinking in terms of distributions. Let's write a little bit of code. Our end goal here is to generate a bunch of realities over and over again and study the distribution of those realities. The best place to start is to just simulate one single reality and make sure we've got it working right. And then we'll do it a bunch of times to study the distributions. So our first step is to think about what numbers are parameters and what numbers should actually follow distributions. So if we look at this, and I'm going to keep this pretty straightforward, we could think about the number of people insured as 200. We're not going to let that vary. The number of people insured is just going to be 200. I'm also not going to let the claim probability vary yet. It's just going to be 5%. But when we get, so these are scalars, that's a deterministic number, right? But where we're going to introduce the stochastic piece for this first part is in the claim amount. So for the claims, instead of saying, okay, the average is going to be 2,000, we're going to presume claims follow a log normal distribution with specific parameters, and that somebody could have, any of those values. So on average, they would expect to have the mean, which is going to be about 2,000, 7.1 on the log scale, log normal scale. But they could have higher or lower according to the specified distribution. So when we start to do this, what we need to do is pick a distribution that we think is reasonable for the underlying parameter, in this case, claim amounts, and parameterize it directly. So we've done that here, and we use NumPy to do so. So NP is the NumPy module. There's a submodule under NumPy called np.random, and there's a bunch of distributions available there. If you're curious to look those all up, you can actually just Google NumPy random. And if we Google NumPy random, you can see under the numpy.org references, we've got the random submodule. And here's all of the distributions that come by default with NumPy. all of these have some sort of random generation associated with them. So any of these you could just take off the shelf and use in these sorts of stochastic models. There are some Python packages that offer some more obscure distributions as well, but I'm not going to cover those today. So I've picked the log normal, but of course you could build this from different random distributions, random variable distributions. Okay, so now we're going to simulate a large distribution of these, and I'm going to do of size 10,000. So that's 10,000 people coming out, and look at this distribution of log normal claims. So if I simulate 10,000 draws from the random variable, the first one was $779, the second one was $732, the third one was $761, and so forth, and there's 10,000 of these. If I look at the average of this distribution, it's pretty close to the $2,000 that we were sort of started with. So the expected value of the distribution, the mean, the first moment, is $2,000 roughly, about 1,976. But what does it actually look like? Well, let's use Seaborn, which is a plotting package from Python, to understand the shape of the distribution. So on average, claims are 2,000, which is going to be right here. That's 20,000, going to be right here in the middle. But because it's a skewed distribution, that's not really like the middle, right? It's because it's a skewed positive only distribution. It's not symmetric. The average is sort of this strange spot based on the skew. So this is what we're really saying. We think claims usually are relatively small. They could be larger, but they become infrequent the larger they get. And there's some really rare claims that are very high, but they're very infrequent compared to the smaller number of claims. So this is a fairly simplistic assumption that the claims follow this distribution. And of course, you would want to examine your data and figure out what distributions they really is reasonable to presume they follow. And then you could implement them using that random module from NumPy. Okay, so that would be our stochastic element for the cost of the claim. The second thing we want to think about is, well, does somebody have a claim or not? If we wanted to leave that as a deterministic model, we could just assume there's a 5% chance of having a claim. So exactly 5% of people will have a claim. But that's probably not true. Even if there's a 5% probability on average, we could have an unlucky year and have more than 5% claims, or we could have a lucky year and have fewer than 5% claims. So this is another source of variation in our outcome that we weren't recognizing when we considered a deterministic model. So if we do that, we could say, okay, let's presume it follows a binomial distribution where we have a 0-1 outcome. P is the probability of a 1 in a binomial distribution. It's kind of like a coin flip. And so we're going to say, okay, if P is equal to 0.05 right there, and we only have one potential event, and we do this 10,000 times, we would expect on average to get 5% of these to have a claim, but each individual person either has a claim or not. Right? So it's the same sort of thing we just did with the log normal distribution. And that's the code we would use in NumPy to do that. And we look at these claims, the average is 5.6% as expected, close to 5%. And we could use Seaborn to look at the distribution as well. All right, so these are our underlying random variables that we're going to combine now to generate our stochastic equation, which is still fairly basic. If we want to include these in our calculations, we can sort of build up by hand our outcome based on these. So if we have a portfolio of size 200, our claim yes or no, instead of it being just a 0.05 chance, we're now going to draw from the random distribution with a 5% chance from a binomial distribution. The size we're going to draw is going to be those 200 people, the number insured. And the claim amount is going to be a log normal distribution. And again, we're going to draw 200 people from that. So if we look at the result, the shape of these objects, they are going to be of length 200 as expected, because there's 200 people in this theoretical portfolio. For each person, we have claim yes or no, 0 or 1, and then we have claim amount, which is going to be that log normal distribution. So if somebody has a 0, they don't have a claim, so their cost should be 0, their claim amount. I'm going to simply multiply claim yes times claim amount, so that claim amount 2 is going to be a 0 if they didn't have a claim, and it's going to be 1 times their claim amount if they did have a claim. So this is now the total number of claims for this single group of 200 people based on a single random draw. And in this case, the total payout is going to be $24,700 for this one version of reality, right? One draw from the distribution. The total payout per person is going to be $123. All right, so these are all of our components, our basic pieces. If I look at the distribution of the claim amount, it's actually going to be mostly zeros as expected, because 95% of these people don't have a claim amount, so it's zero. And then the 5% that do have a claim amount are going to have this skewed distribution of claims. And that's a basic Seaborn distribution plot showing that. Okay, so those are our basic ideas, and these are things you're probably familiar with if you have a background in financial analytics, but maybe you haven't done them in Python before. So if those are the building blocks of our random variables, now we can set this up as a simulation. So I'm not interested in simulating once and saying, okay, we did this exactly once, and here's one potential version of my average costs. What I really want to do is simulate this over and over again and understand all the edge cases. You know, how likely is it for me to have a year where we have a really high number of costs, even if the average is what we expect it to be? We want to study the width of the distribution to understand the edge cases. So we're going to do that by running Monte Carlo simulations from this stochastic equation we've just defined. We introduced two random variables, which is that binomial distribution for the probability of an event occurring, and we use the log normal distribution for the claim amount. So we'll call that a stochastic equation because there's random variables as components of it. All right, so let's continue on. We've done this once, but now I want to build our code up to do it multiple times so that we can end up with this, I might say, posterior result from the model, which is a little bit more Bayesian speak, that will allow us to summarize what we can expect under this stochastic system. So we're going to run it a bunch of times. What does a bunch mean? Well, I'm going to show you the number of reps and how it changes. In general, we want to run this enough times that our results don't change appreciably, even if we run it more times. So what is that number in practice? Well, it really depends on how interested you are in the edge of the distribution. We'll talk about that more in a moment. For now, we're going to start with just 10 reps to see how it works. Another thing to note, I'm going to do this in a vectorized fashion. What that means is we're going to leverage the vectorized nature of NumPy, i.e. We don't have to use for loops. We're not going to have to say for 1 and 1 to 10 for these 10 reps. We're just going to do it over and over again internally through the vectorization. So one way you might think to do this would be to say, okay, for in reps 1 to 10, repeat the simulation. But instead, I'm going to say there's 10 reps, and I'm going to give the size of this binomial distribution to be a 10 by 200. So there's going to be 10 rows and 200 columns. So that means each row is a separate simulation, and each column is a separate person in our portfolio, generating a large matrix. This is a good approach if you can fit all of this data in memory. If you're doing a really large sample, you might need to use a for loop as opposed to generating the rectangular matrix, because this could be a really large data object to hold in memory. But if you're not running out of memory, totally fine and probably fastest to do it this way. Same thing with our log normal claim amounts. We've got a size here of in reps by number insured. So again, that's going to be 10 by 200. That'll give us our 10 simulations. So now that we have rectangles, it's actually pretty easy to just use matrix multiplication rules to do what I did before when we just had a single number. So if I do claim yes times claim amount, under the rules of matrix multiplication, we're going to get the correct distributions here. And so we're going to see that if somebody had a 0, they're going to be a 0. If they had a 1, which is only 5% of them, then they'll have some amount. And so that's what that looks at for these first 5 people. As expected, the shape of that final object is 10 by 200, 10 simulations for 200 people. All right, the final piece of this, and since we're using sort of a single data object, we can just sum it up by row. So if each row is one simulation of 200 people, the sum of each row is going to be our total costs for those 200 people for that simulation. So there's 200 columns, one for each customer. There's 10 rows, one for each repetition of our simulation. And if I do a np.sum, and I say axis equal 1, that's going to give me the sum by row. It's like a marginal sum. And that gives me back the total cost of claims for each of the 10 simulations. If I wanted to calculate the total payout per person, it's just going to be that claim amount summed up divided by the number of insured. So what we're seeing here now is the variation across 10 simulations in the actual costs of this portfolio. And again, these are things you might already be familiar with this sort of approach, but perhaps you've just never done it in Python before. All right, I'm going to pause for just a moment, and I'm curious if anybody has any initial questions. Feel free to post a question in the question window, and I should be able to see it. And I am happy to answer it if you have it. So I'm not seeing any questions yet. I'll probably continue on in about 30 seconds. Unless somebody has a question, feel free to post it in the question window. And actually, go ahead and post at least one, just say, hi, I can hear you. Make sure everybody can still hear me and we're all good to go in the question window. All right, I got at least a couple of still here's. So let's move forward then. Perhaps these things are all familiar to you, but maybe not in Python. So what we've done now is we've generated a large rectangular object that represents the outcome of interest under a stochastic equation with 2 random variable elements. Each column is one person in our portfolio. Each row is one iteration from the simulation. I now want to ramp this up to thousands of iterations and study the outcome. I started with 10 so that you could easily see the shape and understand what we're doing, but 10 is way too small. When we're doing this, we really need a large number of simulations. And the computer's pretty fast at doing this, so it's pretty easy to crank it up. We can do 5,000 or 10,000 or 100,000, that sort of thing. The main thing is the intermediate data size. So right now, the coding approach I have chosen is to use vectorized NumPy data objects. That is the fastest way to do it, even though we're using Python, which is maybe a high level, sometimes slow language compared to like C. The NumPy functions are all compiled C codes. They run really fast. So this is the fastest way to do it, unless you run out of memory. So it occurs to me that, if I'm going to do this 5,000 times, I'm going to have a matrix of size 5,000 times the portfolio size, right? That's my intermediate data object. So eventually you might run out of memory, the bigger that number gets. And if you do, you just might have to do a for loop instead of this vectorized version. So the second consideration here then is, well, how big is enough? How long do I need to run this for? And that really depends on what you're trying to study. In general, if we're interested in studying the middle of a distribution, the median, the mean, the part where there's a lot of mass, then we don't need as many simulations. If you're very interested in studying the edges of a distribution, like the 95th percentile, or the 5th percentile, the edge cases, there's not a lot of mass there. So even when I do this 5,000 times, a small number of those 5,000 times occur at the edges. So if I'm interested in studying the edge, I often have to ramp this number up until I get stability in my estimates. So what you can do is just keep ramping it up and seeing, okay, if I do it 5,000 times and then I do it 9,000 times, that I get pretty much the same answer. And if I see a lot of variation in my answer, that tells me I'm still experiencing what we would call Monte Carlo error, MCMC error, which basically means I don't have enough samples to have stability in my estimate of that part of the distribution. So I'm just going to do this 5,000 times here, but keep in mind that's a piece you probably want to do. I have a question from somebody on the webinar. Do you know whether we can download Jupyter Lab on our work computer or would it have to be on our own PC? Yeah, it really just depends on your organization. I've worked with, a lot of large companies in the US and government agencies. that have the Anaconda distribution on their approved software list. So I guess it just depends on your local policies in your workplace. But what you would do is you would say, ask somebody internally, can I get this Anaconda Python distribution installed? And there's a free version, this open source version here. And if not, then I guess you would have to do it on your personal computer. But I think many companies are using some version of this Python distribution, so you're probably going to be able to get it installed. Once you do have it installed, you can run this Jupyter Lab in your computer, work computer or home computer. It's just comes straight from that distribution. It's a good question though. Somebody just asked about that. Any other questions? Feel free to ask them. I'll keep an eye on the question window. Oh, you're welcome. All right, so let's ramp this up and think about it. I'm still going to consider the number of insured to be 200. This is what I would call a fixed parameter in my model, right? This is not variable. There's no distribution. It's not like some years I have 190, other years I have 220. It's always 200. You could make that a distribution, but I've chosen not to. The probability of a customer making a claim is 5%. I am going to use the binomial distribution to draw from this probability, but I'm assuming that the probability is 5%. You could even add a distribution for this probability, right? You could say, I think it's 5%, but it could be 3% some years, it could be 7% other years. And you can there's really no end to how many ways in which you could add another level of hierarchy to these sorts of simulations. I'm gonna run this 5,000 times. My claim yes or no is the first thing I'm gonna simulate. So we'll do a binomial distribution under the p equal 0.05, that probability of claim. The resulting data structure from here is going to be of size 5,000 by 200, because that's what I've asked for. The claim amount is going to be size in reps by number insured, right? So 5,000 by 200. I'm going to multiply them together as I did previously. I'm going to get claim amount number 2, and then I could get the total cost, that's the claim sums, and the claim per person. So this follows exactly the code we wrote earlier, but now I've got 5,000 versions of this, right? So these final numbers should be of length 5,000. Across the 5,000 simulations, what was the cost of the portfolio and what was the cost per person? All right. Once I've generated this larger sample of results, right, potential realities under the stochastic equation, I can look at the distribution of these claims and start to summarize business relevant questions like how much money we might potentially pay out, how infrequently we would pay out a small amount of money or a large amount of money, right? Not looking just at the average amount, but looking at the variation, the edges of the distribution. So as expected, the average claim payout across these 10,000 reps is going to be close to what we thought it was at the beginning of the simulation. But there's wide variability in how much we might actually pay out. So the width of this distribution is maybe something we really care about, and I would interpret as how variable potential payouts are given the underlying stochastic equation, right? The variables we assigned in the equation. So the mean is, once again, it's right at 20,000 as we expect it to be, but it possibly could be less than 20,000 or more than 20,000, and this distribution, this density, will allow us to make inference on how likely we think it is that we only pay out $100 or we pay out $40,000. So that's what we're going for. The average is interesting, but usually I care about my risk of losing money, having a bad year where I paid out way too much and we actually lost money. So one way to think about that is the percentiles of this distribution. So a question is, let me see if I should say this right. 90% of the time, I expect our total claim payouts to be this number or less. So what is the number for which 90% of the time our payouts will be this number or less? That's simply going to be the 90th percentile of this posterior distribution. So I can use NumPy, calculate the quantile, ask for that 90th percentile, and that number is going to be 32,000. So $32,208, 90% of the time under my model, I expect to pay out this amount or less. The 95th percentile of the distribution is easily calculated, just change our argument slightly to the quantile, and we're going to pay out $37,500, 95% of the time or less. I can repeat these summaries looking at the average claim per person, which is just a scalar offset, right? That's going to be the same thing divided by the total. And so our mean of claims per person is $98, and the distribution of those claims per person looks like this. And I could then summarize the 90th percentile of that distribution. All right, so 90% of the time we'll pay out 161 or less per person, and 95% of the time we'll pay out 187 or less per person. I'll pause for just a moment. Any questions about those summaries of that posterior distribution, that what I would call the density of our expected output? All right, so not seeing any questions, but feel free to put them in and we'll walk through them. Oh, you're welcome, Huma. I appreciate that. Okay, so alternative interpretations of this posterior, let's think about profits and setting expected profit margins and calculating risk of different profits. So the original question was, well, about pricing. If I were to charge $150 per person, what are my profits going to be? Right, well, we could do the average, but I'm also interested in the edges of that distribution. So if I charge $150 cost per person, what are my profits? Okay, well, premium is $150, revenue is this, profits are going to be revenue minus our claim sums, right? That average. So, oh, actually, I should say, when I do revenue minus claim sums, remember, claim sums is of length 10,000. So this is going to be the profits for each of the 10,000 iterations. So if I charge $150 per person, I will generate this much revenue. And then I compare that against the 10,000 simulations. And this revenue is just recycled across all 10,000. So now profits is going to be a vector of length, I'm sorry, 5,000. We did 5,000, not 10,000. Profits will be a vector of length 5,000. So those are the profits, corresponding to these distributions we've been looking at. And it's really easy to write that. All right. So the profits would be different depending on the value that comes out of the simulation, right? Our profits on average are going to be pretty good. They're going to be $10,000. That's the mean profits across those simulations. But again, we care about the edge cases. So let's look at the distribution of these profits and say, well, how often would we lose money? Or how often would our profits be at least a certain amount? And what premiums do we need to charge to ensure our profits are a certain amount? So we can do that again easily with Python code. We look at the distribution of profits. That's the function from Seaborn to look at the distribution of the profits. And we can see that, yeah, on average, our profits are going to be right here, which is good, but it's kind of skewed. And there's a non-significant proportion of the time below zero where we actually lose money. So that's not good. So what proportion of the time are we going to lose money under this simulation? Well, if we consider this to be the posterior density, right? This is now the estimate of profits. If we charge $150 per person, that's our premium under our simulation. We could just count up, okay, of the 5,000 iterations, what proportion of them are my profits less than zero? So this is the Python code to do that. We could say np.sum, profits less than zero. This is going to generate a true false. Is our profits less than zero, yes or no? True or false? I sum up the trues, which says basically how many times are profits less than zero. I divide that by the total number of things in this distribution, which is 5,000, and that's the proportion of the time these numbers are less than zero. It's basically the area under the curve where the curve is less than zero compared to the total is usually the way we would think about that empirically. So under these distributions, even though we had a good average profit, 13.1% of the time we would lose money, which is probably not ideal. All right, an alternative perspective we might say is then to say, okay, well, how much money do I need to charge to ensure that 95% of the time I will make money? Yeah, I might have a loss 5% of the time, but 95% of the time we need to be in the profit. And of course, you could also set, a threshold to say a profit of at least a certain amount. So we can use this simulation to answer this question, but we now need to generate a range of premiums, right? So we're saying, how much do I need to charge? Well, let's say we charged $150, we lost money 13.1% of the time. Okay, well, let's say we charge $160 and so forth. So what I'm gonna do is generate a list of potential premiums we could charge, and then calculate for every single one of them what proportion of the time we would lose money. All right, so to do that in Python, we want to modularize our code, which means I'm going to write a function that calculates the proportion of time we lose money, and then I'm going to reuse it over and over again. This is the basic Python code for writing a function. We define our new function that's called probability of loss. It takes in the arguments of premium, number of people insured, claim sums, that's going to be our total amount of claim costs, and then it returns the profits. So the profits are going to be the number insured times the premium minus whatever the sum of the claims are. So that's my profits. Then the proportion of losses are going to be the sum of the times the profits are less than 0 divided by the shape, right? So this is the code we just wrote a moment ago, turned into a function. So now that I've turned it into a function called prob_loss, I can simply run this function over and over again across a range of premiums and explore the outcome. I'll pause for just a moment. That was kind of a big step. Let me know if you have a question. I'll pause for just a moment so you can look at the code in case you have any questions. Somebody did just ask, is this recorded? And I believe it is being recorded. We'll be able to share it at the end. All right, so we've got this function to calculate the probability of a loss occurring. I'm going to test it now, and I'm going to say, okay, if we charge $120 and there's 200 people, and here's my posterior, what's my probability of a loss? Well, it's going to be 26% of the time. So what I'm going to do now is basically do in Python what would be a for loop. We're going to say, okay, well, for a bunch of different premiums, 100, 105, 200, and so forth, what is my probability of loss? So I'm going to start by generating possible premiums. That's going to be a numbers between 100 and 500 by 1. So we're going to say, okay, if we charge $100, what proportion of the time do we lose money? We charge $101, what proportion of the time do we lose money? $102, what proportion of the time do we lose money? And so forth. The way in which we can implement this for loop in Python is something called list comprehension. So if you've never coded in Python before, we're really covering a lot of Pythonic things. But what this statement right here does, that's a for loop in Python. There's also for loops in Python. You could write a for loop here. But what you can do instead of writing a for loop is just say, for I in premiums, evaluate this function and return a list. That's what that does. And then I turn it into a NumPy array so we can use it in our NumPy language. So in one line of code, I've generated that for loop, applied the function, and got back my probability of losses. And I have my premiums. I can now make a plot to say, for the premium I charge per person, under my stochastic equation, what's the probability of losing money? You know, having profits less than 0. And of course, up here, we could have changed this to be some number other than 0. We could even make it an argument in the function if we had a minimum profit other than 0 desired 95% of the time. So if we charge $100, we're going to be profitable, but not 100% of the time. You know, more like it's going to be 1 minus this number, right? So we would lose money 43% of the time. If we want to ensure we make money at least 95% of the time, it looks like it's going to be right around here. And we could even just ask for that exact number along this curve. So where is the first number where this curve gets below 0.05, i.e. less than 5% chance of losses? And that corresponds to this question: what is the lowest premium I can charge where my probability of having a loss is less than 5%? I could say, okay, well, let's look at these premiums. Let's subset the premiums to the ones where the probability of loss is less than 0.05. And let's calculate the minimum number from that subset. Again, this is just standard Python code. Minimum number is $188. So if somebody were to say, under the stochastic equation, how much money do I need? What's the minimum amount of money I can charge such that I would be profitable 95% of the time? Potential realities, I would say $188 per person. All right, the exact probability corresponding to that is 0.0498 under our CERT simulation of these 5,000 people, and that would be our response. Okay, that's the end of the code that I want to walk through with you today. So I'll have some conclusions about this. This is our first Monte Carlo simulation that we've implemented. It includes a stochastic equation, allowing us to understand variability in our outcome. So what's so important about this is that what we have just done is study the entire distribution of the outcome, which is very different than studying the mean of the outcome. So I feel like we start off pretty trivial here. I say, oh, if we calculate these three numbers, you get the mean. But a big point I want to make, let's start with a question for the group. If you fit a linear regression or even a very fancy supervised machine learning model that's predicting the expected outcome of some continuous process, right? We could do this in very fancy ways. We could use deep learning. If the thing I'm predicting is the expected value of y, what I am studying is the behavior of the mean, the behavior of the mean. I'm going to argue that that is insufficient in many contexts, because what I'm interested in most business contexts, in particular in summarizing portfolio risk in an insurance context, is not the mean. I'm interested in the edges of the distribution. And if I fit models for which the outcome, the thing I'm conditioning on, the thing I'm studying, is the expected value of y, I am studying the mean. So what are the alternatives? Well, what we've walked through today is a way to do this with Monte Carlo methods, where we just dictate a stochastic equation, right? I didn't look at any data. I just said, here's the way I think it works. Here's the parameters for the distribution. Let's simulate from it. That is allowed us to study the outcome, the full distribution of the outcome, but it's not actually conditional on observing any data, right? I think a natural question from here would be to say, well, you know what? I have a bunch of data from last year. Not everybody has the same probability of loss. Not everybody has the same probability of an amount of loss. How do I add in observed data to this sort of work? And so I'm curious, does anybody know the answer to that question? Like, how would I do this sort of work, study a full posterior distribution of results, and then, do it across 5 or 10,000 different versions, but do it conditional on observed data? The answer is not machine learning or, parametric models like linear regressions or generalized linear models. So I see a question, Ryan says, sample from your observed data. Darius says, what if you assumed wrong and the costs are not log normally distributed? Yeah, these are all problems. So Darius, I'm gonna come back to your question in just a moment about our assumptions of the shape of the random variables. So Ryan, you said we could sample from our observed data and then look at the observed data to try to inform what? What are the things you think we need to inform if we're sampling from our observed data? It's going to be these parameters, right? So I've set up a system and I've made a number of assumptions. My assumption is that everybody has a 5% probability of making a claim and that distribution is binomially distributed. That's a strong assumption. I've also made an assumption that the claims are log normally distributed with a mean of 7.1 on the log normal scale and a standard deviation, that sigma of 1. So the way in which we actually condition these things on data, that's what Bayesian inference is all about. So I don't know how many of you are very familiar with Bayesian methods as opposed to what we would call frequentist methods. But Bayesian inference is doing this sort of thing, but then conditioning it on observed data. And then the simulation we pull at the end, this posterior distribution, is actually a combination of our assumptions about how the system works, and then the actual distribution of data that we've observed from our prior years. So it's a little bit of a teaser for learning Bayesian inference. I tend to think of Bayesian inference as sort of like Monte Carlo methods on steroids. In this Monte Carlo simulation, we just decided what to put into this stochastic model, which is still better than only studying the mean. But Darius, you made a great point. What if I assume wrong? What if these assumptions are wrong and the cost is not log normally distributed? We could look at the actual distributions of cost. We could try to fit a log normal distribution to the claims. And if it's a bad fit, then we're going to have a bad model. Our results are going to be not correct. There's going to be bias in them. So then we would say, okay, well, what distribution actually fits costs? And we would basically be looking through different defined statistical distributions until we found one that we think is a good fit for the observed data we have. Once we've done that, we can then use it. Furthermore, not everybody's going to have an equal probability of claim, right? I just said everybody has a 5% chance. We know that's not true across the portfolio. So there's things we're allowed to price on, there's things we're not allowed to price on, but we could still use to understand, risk of a portfolio, even if we can't dictate different prices conditional on those variables. So we could think about estimating a separate P for each person based on their traits. And that's where you get into Bayesian inference. We basically define models like this. We define a hierarchy of random variables that are all linked together that eventually result in our outcome, which in this case is claim sums. We then make some assumption that could be quite strong, or it actually in a Bayesian context, it could be quite weak. We could say, I don't really know what the probability of a claim is. It could be 5%, it could be 95%. So I'm gonna allow an uninformative prior assumption and let the data tell me what the probability is. Same thing with the log normal distribution. So that's a whole nother topic. Honestly, you could spend, weeks learning the basics of Bayesian inference. That's something I think you should look into, and we'd be happy to teach you about it at a later date though. All right, we got about 4 minutes left. I'm gonna go ahead and conclude here. At the very end of this, I've included a few natural extension challenges. We'll be happy to provide this notebook or HTML to you. So if you did want to try some of these on your own, extend some of this code, you could try to fill in these last bits of Python code based on the prior bits of the lecture. I'll go ahead and be quiet for the last few minutes here, but if anybody has any questions, please feel free to post them in the question window or let us know. Oh, Joseph, thank you so much for your comment. I appreciate you saying that. Oh, Ryan Huma, thank you so much. Alex. Ryan Webb. So Ryan says, have you used packages in R to do the same thing you showed here? Yeah, absolutely. Actually, I code, and you probably see my RStudio icon over here. I don't know if you can see it. I code in R a lot, maybe more than I code in Python. So you can 100% do this in R as well. R has more statistical distributions as part of the base functionality. So there's like the stats package in R and then all the RAND functions. So you don't have to like download NumPy, right? There's a matrix data object already in R. But yeah, you could do all of this in R as well. And then of course there's nice visualizations in R that would be very similar to what we did with Seaborn here in Python. Could you code this in SAS too? Darius said, yeah. So I used to, when I was in grad school, I only coded in SAS. I probably prefer coding in R and Python because what I really like is these vectorized calculations. So like in SAS, if you were going to do something like this, you would have to have a data step, right? You'd say you'd initiate a data step, you'd bring in the data set, you got to merge them together. If you want to do a subset, you'd have to put in the subset argument, and then you'd export the new data step. In Python and in R, everything is an object, so you don't have like a data step, right? You just have the premiums object, and you have the probability losses object, and you can just use them together like this and pass them directly into the minimum function. So I tend to really prefer that to the SAS approach personally, but I've certainly done this sort of thing in SAS before, and that's all I used to do in grad school. It's an absolute pleasure to talk to all of you. Anybody still on? Thank you so much. I'm gonna go ahead and drop off. Have a great day.